Welcome back to the Deep Dive, the show dedicated to helping you navigate vast amounts of information without getting swamped. Imagine you're in the data bender's workshop, right? Surrounded by mountains of raw, unorganized materials. You don't just need to move them, you need to shape them, refine them, discover their hidden potential, all while making sure not a single valuable piece gets lost. This isn't just about managing data, it's really about mastering the craft, extracting incredible insights and ensuring every transformation is flawless. Okay, let's unpack this. Today, we're diving deep into the powerful world of SQL. It's the language that truly lets us mold and transform raw data. We've compiled a fantastic stack of sources covering everything from its core principles all the way to advanced optimization techniques and even its future trajectory. Our mission here, to equip you with the essential knowledge to not just understand, but truly master the art of data manipulation.
Yeah, and what's truly fascinating here is how SQL has become this kind of silent force, the very backbone orchestrating nearly all modern data systems. I mean, from your online banking transactions to the complex algorithms behind scientific research, SQL is there, working behind the scenes. So this deep dive, it'll provide you with a shortcut, really, to understanding critical database concepts, helping you quickly gain knowledge for, say, upcoming meetings, essential projects, or maybe just to satisfy your pure curiosity, right? All without that overwhelming information overload that often comes with such a powerful topic. We're going to explore its hidden complexities, sure, but also the elegance of its solutions, making sense of how to effectively bend data to your will.
Okay, so before we start crafting our data, bending it, we probably need to understand the history of the tools we're using. SQL isn't some brand new tech. It has an incredible story of resilience, adaptation. So what's his journey? How did it come to dominate the data world like it has?
It's quite a journey, yeah. If we look back, way back to the early days, before SQL really revolutionized things, database systems were, well, vastly different. Picture a hierarchical database system. The data is organized in these pretty rigid tree structures. Our sources actually give an example, George Blake's bank accounts. You might have customers as the main branch leading to accounts, then branching further to transactions. Now, this model worked, but imagine a programmer trying to find one specific transaction. They had to navigate these rigid structures step by step. They needed to understand the exact path the data followed. It was cumbersome and tightly coupled to the physical storage.
So it's like trying to find a specific book in a library where all the books are stacked in just one really complex tower based on when they were acquired or something, and you have to climb through the whole structure just to get what you need. Sounds very inefficient.
Exactly. That's a great analogy. Then came the network data model, like the Codacil model. It was an evolution, definitely. It extended the hierarchical approach, allowing a record to have multiple parent-child relationships. So it created a more interconnected web.
Okay, a bit better then.
A bit better, yes. But programmers still face the challenge of navigating record by record, understanding all those explicit links. You still needed to know the precise path. It was still very much like a complex, manually organized filing system. The real game changer, though, arrived in 1970. Dr. E.F. Codd's relational model. He simplified everything. He proposed that all data be represented as simple, logical row and column tables.
The tables we know today.
Precisely. It was an elegant solution because it separated the logical view of the data from its physical storage. That made data so much easier to manage and query. Suddenly, that complex filing system was replaced by, well, like you said, a highly structured cross-referenced library. Every piece of information in a clearly labeled book organized into logical, accessible sections.
And that's where SQL stepped in, right? As the sort of universal language to talk to this new elegant library.
Exactly. IBM's System R project was really instrumental in bringing this concept to life, eventually leading to SQL Data System in 1981 and, crucially, Database 2, or DB2, in 1983. DB2 became IBM's flagship relational database management system. And with IBM's significant influence back then, SQL rapidly became the de facto standard database language. Its vendor independence was a massive advantage. Our sources really highlight that SQL-based databases and programs could be moved between different vendors with minimal conversion effort.
Wow, yeah. Little retraining needed too, I bet.
Right. That fostered its widespread adoption across industries. You weren't locked into one vendor's ecosystem quite so tightly. The initial ANSI standard for SQL in 1986 was actually pretty small, less than 100 pages. But as SQL kept evolving and incorporated more advanced features, the SQL NE2 standard, approved in 92, grew to nearly 600 pages.
Quite a jump.
It was. This expansion marked a significant increase in complexity, sure, but also in rigor. It showed SQL's continuous adaptation its maturation as a robust, comprehensive data language, and this ongoing standardization ensured SQL remained the universal tool for data management that it still is today.
That elegance you mentioned, it seems to boil down to how SQL organizes data into tables.
Hmm.
Simple, logical tables. But to truly bend that data in our workshop, we need to understand the fundamental components. What are these tables actually made of? And crucially, how do we tell them what kind of data to hold? Because like you said, you wouldn't put flour in a liquid measuring cup, right?
That's a perfect analogy for data types.
Yeah.
At its core, the relational model organizes data into tables, and tables are made up of rows and columns. A row represents a single entity. Think of a single sales office in an offices table. All the data in that row applies to that specific office. Each column, on the other hand, represents one specific piece of data for each entity, like the city, or the sales figure, or the MGR ID for an office.
Okay, rows are the things, columns are the attributes of those things.
Pretty much. Now, to uniquely identify each row in a table, we use a primary key. Think of personaed in a person table. It's a column, or maybe a set of columns, whose values uniquely identify each row. This guarantees no two entries are exactly alike. It's crucial for preventing duplicate records, maintaining data integrity.
Got it.
Then, to create meaningful relationships between tables, we use foreign keys. A foreign key in one table, let's say reap office in the sales reps table, links to the primary key, maybe office, in another table, like offices. This establishes a clear parent-child relationship. It defines how different pieces of data connect across your entire database structure.
So primary keys are like the unique serial numbers for each item in our workshop inventory. And foreign keys are like labels on those items saying, this belongs to category X, pointing directly to the main category list, ensures everything's linked up properly.
Exactly. That's a great way to visualize it. We define these structures using SQL schema statements, primarily the create table command. Once the table structure is defined, we populate it with data using SQL data statements, like insert. And all these definitions, the table structures, indexes, views, they aren't just floating around. They're stored in a special set of tables called the data dictionary, often referred to as metadata, basically, data about the database.
Ah, so the database documents itself, in a way.
Precisely. You can even query this data dictionary using a select statement to discover the current database structures, understand its schema. Now, back to your measuring cups analogy. That's exactly where data types come in. They tell the database precisely what kind of information each column is designed to hold, prevents mismatches, ensures integrity. For character data, text, you have charm. That's for fixed-length strings. Good for things like, say, state abbreviations, always 2 characters. Then there's varchar for variable length strings, much more common for names, addresses, where the length varies, save space.
Right, more efficient.
Yeah, and for really long strings, emails, descriptions, maybe XML documents, there are various text types, tiny text, medium text, long text. They handle huge volumes of character data way beyond standard strings. For numeric data, you've got float and double E for approximate floating point numbers, useful for scientific data measurements. But for precise financial calculations counts, you typically use integer or decimal types, exact values.
Very important for money.
Absolutely. Then temporal data, dates and times. Specific types here too. Date is just the date, YYYYMMDD, good for a birth date. Date time includes time, YYYIMMDD, HMISS, perfect for a transaction timestamp. Timestamp is similar, often with automatic update features, and time is just the time component, HHMISS, for durations or specific times of day. And one more interesting one, enumerated types, CM. These are fantastic for predefined sets of values. Like specifying gender, enum, and MD, it restricts input to only those options. Powerful way to enforce consistency, prevent bad data.
That specificity is fascinating. But what about when we just don't have a value for a column? Like maybe a shipping date for an order that hasn't shipped yet.
That brings us to NNL values.
Yeah.
And they're crucial, really crucial to understand. NLL signifies the absence of a value. It's distinctly different from 0 or an empty string or even a blank space.
So it means we don't know or it doesn't apply.
Exactly. Not applicable, unknown, or empty set. This distinction is vital because NL values behave differently in queries and calculations. They're often excluded by aggregate functions, require special conditions to check for them. You can specify a column as not NLL when you create a table if that column absolutely must have a value, like a primary key.
Yeah.
Ensures data completeness right from the start.
Okay, when we're shaping data in our workshop, bending it this way and that, how do we make sure those bends are stable, trustworthy? Especially when multiple people might be working on the same data set at the same time. It seems like constructing a massive building, you need an incredibly solid foundation, absolute structural integrity.
Absolutely. That stability, that trustworthiness, it comes from the ACD properties: atomicity, consistency, isolation, and durability. These are a set of principles that SQL databases rigorously adhere to. They ensure dependable transaction processing, especially vital in multi-user environments where lots of changes are happening concurrently. Think of them as, like you said, the four main structural beams of our data building. If anyone fails, the whole structure's integrity is compromised, even under stress.
Okay, break those down for us. Atomicity.
Atomicity. This is the all-or-nothing principle. An arrangement, or a transaction, is treated as a single, inseparable unit. Either all the steps within that transaction complete successfully, or none of them do. Think of a bank transfer. Moving money from checking to savings. Either the money is successfully debited from checking and credited to savings, or, if anything goes wrong, the entire transaction is rolled back. No partial transfer occurs.
Ah, critical for banks.
Absolutely critical. It's what fundamentally guarantees trust in operations like that. Your money either moves completely, or the system ensures it never just vanishes. Next, consistency. This property ensures that data always moves from one valid state to another. It maintains all the defined relationships and rules within the database, prevents things like orphan records or data that violates business logic. For instance, if you have a rule that a child record can't exist without a parent, a consistent system stops you from deleting that parent if child records still refer to it.
Unless you specifically tell it how to handle that.
Right, unless you've explicitly configured something like cascading deletes. The key is, the data's integrity and validity are always preserved. Then there's isolation. Incredibly crucial in multi-user environments. It means concurrent transactions don't interfere with each other. Even if multiple users are reading and writing the same data, each transaction appears to execute independently, sequentially. Our sources mention the non-repeatable read problem. That's where a program might see inconsistent data within its own transaction because another user committed an update midway through.
Yeah, that would be bad.
Very bad. Isolation levels are designed to prevent exactly those kinds of issues. It provides a consistent, predictable view of data for each user, even in a chaotic multi-user system, like multiple people editing a shared document without seeing each other's half-saved changes constantly popping up.
Okay, makes sense. And the last one, durability.
Durability. Once a transaction is successfully completed and committed, its changes are permanent. They survive system failures, power outages, any other unexpected events. The data is written to stable storage, it won't be lost. This is the promise that once you've made a data bend, once it's committed, it's there to stay, regardless of external disruptions.
So commit and rollback are our ultimate data bender controls for orchestrating these properties then, the levers we pull.
Precisely. Commit is the signal for success, makes all changes permanent and durable. Rollback, on the other hand, aborts a transaction, backs out all changes made since the transaction started. That effectively ensures atomicity. Some systems even offer save transaction or save point for partial rollbacks within a larger transaction, giving you even finer control. These mechanisms, commit, rollback, save point, they're the bedrock for reliable, trustworthy data manipulation, all built on those ACID principles.
All right, we've laid the groundwork, understood the structural integrity, the AC properties. Now let's get to the really exciting part, actually grabbing the data we need, the select statement. This feels like where the real magic of uncovering insights begins in our data benders workshop. So how do we best wield this power effectively?
The select statement is absolutely your primary tool for extraction. It's like that meticulous librarian you mentioned. Given your precise request, it pulls specific books, specific passages from the shelves. It can even combine parts from different books, relabel them for you. Its basic syntax is quite straightforward. You specify what data items, usually columns, you want in the select clause. You specify from which tables in the from clause, and optionally, which rows you want to filter using the where clause. So, for example, select city, office, sales from offices. That gets you the city, office number, and sales for each office from the offices table. Simple enough.
Okay, now I know a lot of people just type select doc star, get everything. Is that good practice?
Selecting. It's convenient, especially when you're just exploring or developing. Quick check, see all the columns. But generally for production queries, it's better practice to explicitly name the columns you actually need. Our sources point out it's often faster, more efficient. The database processes less data, sends less across the network.
Right, makes sense. Less work overall.
Exactly. Plus, it makes your query's intent much clearer. Anyone reading your code knows exactly what data you intended to retrieve.
Yeah, I can see how select could cause problems down the line if someone adds a new column to the table later.
Precisely. That's a classic issue. A select written years ago might suddenly start pulling sensitive new data it shouldn't, or just slow down because it's grabbing some huge new LOB column it doesn't need. Convenience bites back sometimes. Now, to make the results even more readable, especially if column names are a bit technical or maybe similar across joined tables, you can use column aliases. You just temporarily rename columns in the result set. Use AS or even just a space, like d.name AS depname or just d.name depname, makes the output much more user-friendly.
Nice. Little labels for the finished product.
Exactly. And you're not limited to just retrieving existing columns either. The select clause is pretty powerful. You can include calculated columns and apply built-in functions directly. Perform arithmetic, manipulate strings, extract parts of dates right there. For example, month, higher date, and year, higher date, can pull out the month and year from a higher date. Or concat can combine first and last names into a full name.
So you can start shaping the data right as you're pulling it out.
That's it, sculpting it right at the point of retrieval, transforming it into a more usable format immediately.
That's great. But powerful as select is, we rarely need all the data it could possibly pull. How do we narrow down that focus? Find exactly what we're looking for rather than sifting through mountains of results in the workshop.
This is where the where and having clauses become absolutely indispensable. Think of them as different bouncers at our data club. The where clause is the first bouncer. It checks individuals at the door, letting in only those rows that meet certain criteria. It filters the raw data based on conditions before any grouping or aggregation happens.
Okay, initial screening.
Right. Then the having clause is like a second bouncer inside. Checks groups after they formed, maybe around tables or on the dance floor. Says, okay, only groups of 3 or more can stay. It filters group data after aggregation.
Ah, different jobs. Got it.
Exactly. Let's dive into the where clause first, because it's incredibly versatile for that initial filtering. You've got basic equality and inequality, where title teller finds exact matches, where pt.name customer accounts finds things that don't match, logical operators, ND or R, combined conditions. And key means all conditions must be true, where title teller and start date 2007-0101 gets only tellers hired before 2007.
Both things have to be true.
Yep, or means at least one condition must be true. Range tests, between. Great for numbers or dates, where order date between 01 Octane 89 and 31 to C 89. That includes orders on those two dates as well. The endpoints are included. Set membership annex. Check if a value is in a list, where a rep office in 11-13-22 finds salespeople in just those specific offices. Not in does the opposite.
Handy for multiple specific values.
Very handy. Pattern matching like. For partial string matches, use a % as a wildcard for any string of 0 or more characters. The underscore matches any single character. So where product like A per C BC % might find products starting with A and having BC somewhere later. You can also use not like. And crucially, null value test. I is not null. Remember, null. You can't test it with or no. You must use I as null or is not null.
Right. Got to check for that absence specifically.
Exactly. And remember, if a condition involving a NL evaluates to NL, that row usually isn't included. So be explicit when checking for NLs. Now, the having clause, this comes into play after data has been grouped using group by Y, which we'll get to next. It filters those groups based on aggregate conditions. So if you've grouped employees by department and want only departments with more than 2 employees, you use having count e.empid2. You couldn't use where for that, because where works on individual rows before the counting happens. Having works on the results of the count for each group.
Okay, that distinction is key. Where filters rows, having filters groups based on aggregates.
You got it. Critical for precise data shaping.
Okay, so real-world data, it's rarely in one neat, isolated package. It's usually spread across different tables. How do we link these different tables together to get a truly complete picture? Like assembling that complex jigsaw puzzle where the pieces initially came from different boxes in the workshop.
That's exactly what joins are for. They are absolutely fundamental to working with relational databases. Joins let us combine data from 2 or more tables by comparing values in common columns. They're how we connect the distinct pieces of information scattered across our data system.
So connecting the dots between tables.
Precisely. Let's look at the main types. Inner joins. This is the most common type. Often just writing join defaults to this. An inner join only returns rows where there's a match in both tables based on the condition you specify in the on-end clause. For example, join employee and department tables on depted. You only see employees who are assigned to an existing department and departments that have at least 1 employee.
So if an employee has no department listed or a department is empty, they don't show up.
Correct. Those records won't appear in an inner join result. Now, if you do want to keep rows, even if they don't have a match, you use outer joins. Left outer join. This returns all rows from the left table, the first one mentioned in the from clause, and only the matched rows from the right table. If there's no match for a left table row, the columns from the right table will just appear as null. Our sources give an example, listing salespeople and their cities, including salespeople not yet assigned an office. You'd see all salespeople, and for those without an office, their city column would just be null.
Ah, so you keep everything from the left side regardless.
Exactly. Right outer join is just the mirror image. It returns all rows from the right table and matched rows from the left. Nulls appear for unmatched left table columns, and full outer join. This returns all rows when there's a match in either table. Shows NLLs for unmatched columns on both sides. It gives you the complete picture of both tables, matched and unmatched.
Okay, inner join is only the perfectly matching puzzle pieces. Left outer keeps all pieces from the left box, even the unmatched ones. That's a really clear distinction.
It is. And as queries get more complex, joining multiple tables, or maybe even joining a table to itself, table aliases become incredibly important. They make the query readable and help differentiate tables, like employee E inner join department V. Using E and D as short aliases makes it much easier to follow which column belongs to which table.
Especially if columns have the same name in different tables.
Absolutely essential then. And they're vital for self-joins, where you join a table to itself. Maybe finding employees managed by other employees in the same sales reps table. You need aliases to distinguish the employee role from the manager role. We should also briefly mention natural joins. They're a shorthand. They rely on identically named columns in both tables to figure out the join condition automatically.
Sounds convenient, but maybe risky.
It can be. It's less explicit. If column names accidentally match in ways you didn't intend, you can get unexpected results. Explicit joins with on are usually safer. And finally, cross joins. These produce a Cartesian product. Every row from table 1 combined with every row from table 2 creates a massive result set usually. Very niche uses, maybe generating test data or a series of dates, usually not what you want for typical data retrieval. An inner join without an on clause actually does the same thing, often by accident.
Good to know what to avoid.
No.
Okay, once we've understood our data, learned how to pull specific insights using select and join, we often need to actually change it. How do we add new information, modify existing records, or reliably remove unwanted data in our workshop? It's like editing that manuscript, adding new content, revising paragraphs, deleting sections.
That's a perfect way to think about it. We use the insert, update, and delete statements. They're just as critical as select for managing and sculpting our database content. These are your fundamental tools for shaping the actual data.
All right, let's start with adding data. Insert.
Insert statement. This is how we add new rows. To add a single row, you specify the table, the columns you're populating, and then the values, like insert into person, personid, name, name, gender, birth date, values. Null, William Turner M, 1972, date 5/27. If a primary key column is set to auto-increment, you can often provide null as the value, and the database assigns the next unique number automatically.
Handy.
Very. You can explicitly insert NL values too, or just omit columns that allow NLs, and the database usually inserts NL by default. To add multiple rows at once, you can provide a comma-separated list of value sets, or even use a select statement to pull data from another table and insert it directly into your target table.
Ah, copying data between tables.
Exactly. And some databases, like MySQL mentioned in our sources, have neat features like insert on duplicate key update. If you try to insert a row that violates a unique key, instead of failing with an error, it updates the existing row based on the logic you provide. Very elegant for handling existing records gracefully.
Okay, what about changing existing data? Update.
Update statement. This modifies existing data in one or more rows. You use update to specify the table, set the new values for one or more columns, and crucially, you use a where clause to specify which rows to update. For instance, update sales rep set rep office 11, quota 0.9, quota where rep office equals 12. That would move all salespeople from office to 12 to 11 and cut their quotas by 10% simultaneously.
The where clause is critical here too, isn't it?
Absolutely critical. Without a where clause, update would modify every single row in the table. Almost certainly not what you intend. Disaster territory. Update can also trigger cascading updates. If you change a primary key in a parent table, corresponding form keys and child tables can be automatically updated if the constraint is set up with onUpdate cascade.
Keeping things consistent automatically. Nice.
Yeah. Finally, delete statement. This removes rows. A simple example. Delete from sales reps where sales 150,000 by 0.00. Remove salespeople below that sales threshold. And again, the where clause is absolutely, utterly essential without it.
You delete everything, the
Right.
entire table.
Exactly. Every database admin has a horror story, or a near miss, involving a delete without a where. It's the ultimate measure twice, cut once rule in data bending. Like update, delete can also be configured for cascading deletes using onDelete cascade in the foreign key definition. Deleting a parent row, like an office, could automatically delete all its related child rows, the salespeople in that office. Keeps data consistent, prevents orphans.
Wow. Powerful, but needs careful handling.
Extremely careful handling. And all these operations, insert, update, delete, are deeply tied to data integrity and constraints. Primary keys, foreign keys, uniqueness constraints, check constraints like check target equal 0.000 to ensure a target is never negative. They're vital guardrails. They maintain the quality and validity of your data as you add, modify, and remove it. They're the constant protectors preventing inconsistencies during your data bending work.
Okay, sometimes the data we need to filter or compare against isn't just a static value. Sometimes it's actually the result of another query. This sounds like where subqueries come in. They let us perform these multi-stage data bends, right? Almost like asking a complex question to an assistant, then using that answer to ask an even more specific question.
That's an excellent way to put it. A subquery is basically a query embedded within another SQL statement. This allows for incredibly powerful and flexible data manipulation. You use the result of one query as an input or a condition for another. It's fundamental for more complex transformations.
So, queries inside other queries, where do they usually show up?
They can be placed in several key clauses. Most commonly, you'll see them in the where clause for filtering. For example, maybe you want to find offices where their target sales exceed the total quota of all salespeople working in that specific office. The subquery, select sum from sales reps where rep office would dynamically calculate that sum for each office as the outer query processes it.
Ah, dynamic calculation based on related data.
Exactly. They can also be used in the from clause. This creates what's called the derived table. The outer query then treats the result of the subquery as if it were just another regular table, often used for pre-aggregation or simplifying complex joins. And sometimes you see them in the select clause itself, though typically only when the subquery is guaranteed to return a single scalar value.
So it's like a nested instruction set. Allows for really granular dynamic decision-making within a single query.
Precisely. And we usually distinguish between two main types based on their dependency: independent or non-correlated subqueries. These can be executed entirely on their own. Their results don't depend on the outer query's current row. For instance, finding all employees whose IDs are not in the list of supervisor IDs. The subquery just gets the list of supervisor IDs once. A quick note here, be careful how NAL values in the subquery result affect comparisons, especially with operators like not NN. Sometimes it can lead to unexpected empty results.
Good tip. What's the other type?
Correlated subqueries. These are more complex. They are dependent on the outer query. They get executed once for each candidate row that the outer query is considering. Imagine finding customers who have exactly 2 accounts. A correlated subquery would count the accounts for each customer individually, and the outer query would use that count to filter.
So it runs repeatedly for each outer row, potentially slower.
Potentially, yes, depending on the database optimizer. But sometimes they are the most logical or only way to express a condition. Beyond basic comparisons, subqueries often work with powerful operators. The exists operator checks if a subquery returns any rows at all. It doesn't care what the rows are, just whether at least one exists. Often very efficient because the database can stop processing the subquery as soon as it finds one match. An example from our sources: listing products for which an order of $25,000 or more has been received. The subquery uses exists to check if such an order exists for each product. Not exists checks for the absence of any matching rows.
Just a true-false check, basically.
Exactly. Then you have all and NEA, or sum operators. These compare a single value to the set of values returned by a subquery. All means the comparison must be true for every value in the subquery result. Any at or sum means it must be true for at least one value. Example, finding accounts with a balance smaller than all of Frank Tucker's accounts. The balance must be less than every single one of his account balances. And finally, row value comparisons. More advanced SQL versions let you compare entire rows of values, not just single columns. Adds another layer of sophistication.
Wow. Subqueries really open up a lot of possibilities for complex dynamic data bending.
They absolutely do. indispensable for breaking down complex problems into manageable logical steps within a single statement.
Okay, raw data is useful, row by row, but often the real insights come from the big picture, right? The summaries. How do we roll up all those individual data points into meaningful summaries? Like taking that pile of raw ingredients in the workshop and blending them into a smooth output, maybe category by category.
That's a great analogy because that's exactly what aggregate functions do. They operate on a set of rows and produce a single summary value. These are the tools for getting that big picture from your detailed data.
What are the main ones we use?
The most common aggregate functions you'll encounter are max, finds the maximum value in a set, min, finds the minimum value, avg, calculates the average value, sum, calculates the sum of values, and count, counts the number of values or rows. So, for example, if you're analyzing checking accounts, you could use a single select statement with these functions. Max avail balance, min avail balance, min balance, avg avail balance, avail edit balance, subpin amounts, and count new accounts. Gives you an immediate, comprehensive summary of the financial health of those accounts.
Quick snapshot. But what happens with NLL values when you're calculating, say, an average or a sum? That seems important.
It absolutely is. The standard SQL behavior is that sum, avg, min, max, and count column name ignore NLL values completely. If a column contains NLLs, those NLLs are simply not included in the calculation.
So AVG isn't skewed by unknown values.
Correct. But it also means the average is only of the known values, which might or might not be what you expect. The exception is count. That counts all rows in the group or table, regardless of NL values in specific columns. Count column name, however, only counts rows where that specific column is not NLL.
Ah, subtle but important difference between count and count column.
Very important distinction. Now, while aggregate functions can summarize an entire table, their real power often comes with the group by Y clause. Group by Y lets us apply these functions to subsets of data. It divides the query results into groups based on the values in one or more columns. Then it applies the aggregate function separately to each group, producing a single summary result for each group. For example, count how many accounts each employee opened. You'd group by open-emped and then use count in the select list.
So you get a count per employee.
Exactly. You could even do multi-column grouping. Group by Y product CD, open-branched, open-emped would give you, say, total deposits for each unique combination of product, branch, and employee. Very granular summaries. Some database systems, like MySQL, also offer extensions like with rollup. Used with group by Y, this option generates additional summary row subtotals for each grouping level, and a grand total at the end, all within the same result set. Really handy for hierarchical summaries.
And this is where having comes back in, right? Specifically for filtering these groups after the aggregation.
Exactly. We touched on it before, but it fits perfectly here. The having clause is used specifically to filter those grouped results after the aggregation has occurred. So you group employees by department using group by Y, calculate the count per department using count, and then use having count.emped2 to only show the departments that meet that aggregated condition. You're filtering the output of your data blender based on the characteristics of the blended groups, not the individual raw ingredients before blending.
Okay, what if different users in our data benders workshop need to see the same underlying data, but in completely different ways? Or maybe we just want to simplify really complex queries that we run often. Views sound like they offer a way to create custom lenses for our data, almost like personalized dashboards.
That's precisely it. A view is essentially a virtual table. Its contents are defined by a saved select query. It looks and acts just like a real table. It has named columns, rows of data. You can query it like any other table. However, unlike a real table, a view doesn't typically store any data itself.
So it's just a stored query.
Pretty much. The data you see through a view is the result of the underlying query that defines it, executed dynamically every time the view is accessed, usually. The view definition itself is stored in the data dictionary. Views serve several really crucial purposes in our data bending workshop. Simplifying database access. This is a big one. Views can hide the complexity of multiple joins, intricate calculations, or even messy underlying table structures. They present the data in a more natural or simplified way for specific users or applications. For example, a customer totals VW could pre-calculate the number of accounts and total deposits for every customer. A business analyst can just query that simple view instead of writing the complex aggregation query themselves every time.
Makes life easier for the users.
Definitely. Another major use case is restricting access security. Views are incredibly powerful for controlling who sees what. You can create a view that only shows certain rows, horizontal view, based on a where clause in the view definition. or only certain columns, vertical view, hiding sensitive data. Our sources mention a repinfo view showing salesperson, MPLN name, reap office, but hiding sensitive sales and quoted data from the underlying table. Users are granted permission to the view, not the base table. It enhances security by providing a customized lens. They only see what they're authorized to see.
So you control access very granularly.
Exactly. And data aggregation views, as we touched on. You can encapsulate complex aggregate queries in a view. Application developers don't need to rewrite that logic. It just query the simpler predefined view. Streamlines development, ensures consistency.
So it's not just about simplifying, but also about presentation, security, and consistency.
All of the above. Now, it's worth a brief mention that some simple views can be updatable. You can sometimes insert, update, or delete through them. But there are significant limitations, especially for views based on joins, aggregations, or calculated columns. The database needs a clear way to translate changes made to the view back to the underlying base tables.
Makes sense. Probably best to think of them mostly as read-only lenses.
For the most part, yes. They add a powerful layer of abstraction that enhances both usability and security without actually duplicating the underlying data. Custom lenses for your data.
Okay, having all these powerful data bending tools, select, join, insert, views, procedures, it's one thing. But making them run fast and smoothly is another challenge entirely. In the Data Benders workshop, we don't just bend data, we want to bend it efficiently. Why is this efficiency so crucial, and what typically slows us down? SQL performance tuning is incredibly vital because even with the fastest hardware, the most modern relational databases, our sources really emphasize there is always room for improvement. On large-scale data, even seemingly minor changes to a query or a database configuration can have dramatic impacts, positive or negative, on execution times and overall system responsiveness. Imagine our data bending workshop. We might have the best equipment, the fanciest tools, but if our processes are clunky, if our tools aren't sharp, we're still wasting precious time and resources. Efficiency matters.
What are the usual culprits, the things that cause these slowdowns?
There are several common causes of bottlenecks that can turn a smooth data operation into a real grind. CPU bottlenecks, just the processor struggling to keep up. Database configuration problems, maybe poorly tuned settings, or issues lingering after an upgrade. Poor database design, this is a big one. Fundamental flaws in how tables are structured, relationships defined, data normalized. These can cause persistent performance issues that are really hard to fix later.
Getting the foundation wrong? Exactly. Also, just large tables. Processing huge amounts of data naturally takes time. Indexing issues, a lack of appropriate indexes, or maybe inefficient indexes. This can turn a quick lookup into a slow, painful, full table scan. Key issues, problems with primary or foreign keys. Unmanaged complex queries, really complicated SQL that hasn't been optimized by someone who knows what they're doing. Bad coding in applications interacting with the database. And heavy data loads processes that insert or update massive volumes of data can create significant slowdowns too.
It really sounds like optimizing a highly complex, multi-lane highway system. You've got to identify the traffic jams, maybe add faster express lanes, reroute traffic intelligently to keep everything flowing.
That's a perfect analogy. And the underlying architecture plays a huge role too. Our sources highlight the client-server architecture as a significant improvement over older file-server models. In a client-server setup, the user interface stuff happens on the client machine. The heavy data lifting file I/O, query processing, is concentrated on the powerful database server. This drastically reduces network traffic compared to a file server, where the client might have to pull huge chunks of the database across the network just to find a few rows.
SQL acts as that efficient communication protocol between the client and server.
Exactly. It allows for a much better distribution of workload, concentrating the data-intensive functions where they can be handled most effectively.
So how do we tackle these bottlenecks in our Data Benders workshop? What are our go-to strategies for making our data transformations faster, more precise? Like that master chef analyzing a recipe for shortcuts.
Well, when it comes to sharpening our tools for query optimization, there are several proven strategies that can make a huge difference. First, focusing on query optimization strategies themselves. Specific column selection. We mentioned this before, but it bears repeating. Always use actual column names in select instead of Lil. Our sources explicitly state this makes queries faster. Less data to process, less data to send. Simple win.
Okay, no more select in production code. Got it.
Good rule. Query tuning. This is about refining the SQL itself. Writing smarter where clauses, optimizing join conditions, rethinking subqueries for maximum efficiency. It's about crafting better SQL. Good database design. This is foundational. Proper normalization, choosing appropriate data types, defining relationships well from the start. It prevents so many performance problems down the road. And basic maintenance. Regularly updating statistics, analyzing query performance, tracking key indicators. This helps you spot bottlenecks early before they become critical fires you have to put out.
Proactive monitoring.
Exactly. Now, probably the single most impactful technique for speeding up queries is indexing. Purpose. Indexes are special lookup structures. When you search for data on an indexed column, where a column is value, the database can rapidly search the much smaller index to find the location of the relevant rows, then jump directly to them in the main table. This is vastly faster than scanning the entire table row by row, especially for large tables.
Like the index at the back of a book. Find the keyword, go straight to the page.
Perfect analogy. That's exactly how it works. Automatic indexes. Databases usually automatically create an index on primary key columns, essential for ensuring uniqueness and fast lookups on those crucial identifiers. Recommended indexing. Beyond primary keys, it's generally recommended to build indexes on columns used in foreign key constraints. The database often needs to check related rows quickly. Also, index columns frequently used in where clauses, order by clauses, or join conditions, especially things like date columns or short string columns used for filtering.
But there's a downside to indexes, right? They're not free.
Correct. There are trade-offs. Indexes take up additional disk space, and more importantly, they add overhead to insert, update, and delete operations. Why? Because every time you change data in an indexed column, the index itself also has to be updated. So indexes speed up reads, select, but can slow down writes. It's always a balancing act.
Finding the right balance for your workload.
Precisely. You manage them using create index to add one, and drop index to remove one if it's no longer useful or if the write overhead becomes too high. Beyond indexes and query tuning, monitoring and analysis are key. Tools like SQL Server Profiler, mentioned in our sources, let you watch performance in real time. You can see query execution times, resources used, invaluable for pinpointing slow queries or operations. And in cloud environments, optimizers are getting smarter. They might collect real-time I/O performance data to make better decisions about how to execute a query, adapting dynamically.
So constantly measuring and refining the process, sharpening those tools.
That's the name of the game for sustained performance.
What if we have a really complex series of data bins, a whole routine that we need to perform over and over again? Can we pre-package that logic in the workshop? Like having a highly skilled, pre-programmed robot assistant ready to execute an intricate sequence of tasks with just a single command.
That's a fantastic analogy for stored procedures. That's exactly what they are. They are sequences of extended SQL statements, often including control flow logic like if-then or loops grouped into reusable programs, stored directly within the database itself. Instead of an application sending, say, 10 individual SQL statements back and forth to perform a complex task, you can make a single call to a stored procedure.
Just one call.
Just one call, passing any necessary parameters. The procedure then executes all that complex logic directly on the database server. The benefits are significant. Reducing network traffic. This is often the biggest win. That single call replaces potentially many round trips between the application and the database. Dramatically reduces network chatter, improves overall speed, especially for slower networks.
Less back and forth.
Much less. Encapsulation. Stored procedures help achieve object-oriented principles, like encapsulation. They bundle up data manipulation logic. They can act as methods for database objects, enforcing business rules uniformly. If a business rule changes, you modify the procedure in one place to the database. All applications calling that procedure automatically adhere to the new rule without needing code changes themselves.
Centralized business logic. Very powerful.
Very. And they offer rich capabilities beyond standard SQL. Conditional execution. IF, then LOC logic. Looping. While loops, for loops, cursor-based loops to process data iteratively within the procedure, returning values. Stored functions, a special type, can return a single value, useful within other SQL statements.
Yes.
Error handling. Mechanisms to catch and manage errors gracefully within the procedure's logic. You define them using a create procedure statement, specifying the name, parameters, local variables, and the sequence of SQL and procedural logic.
Okay, and what about triggers? Are they related?
Yes, closely related. Triggers are a specialized type of stored procedure. The key difference is they are invoked automatically by the database in response to specific events, usually an insert, update, or delete operation on a particular table.
So they run automatically when data changes.
Exactly. They're incredibly powerful for enforcing complex business rules that go beyond simple constraints. For example, A trigger could automatically update sales totals in the sales reps and offices tables every time an order is inserted or modified, or maintain an audit trail. They can also provide extended referential integrity, like implementing cascading updates or deletes if the database doesn't support them natively via constraints. Triggers are like silent guardians, ensuring data integrity and complex business rules are always followed, often completely invisibly to the application making the initial change.
Pre-programmed assistants and automatic guardians. Very useful tools in the workshop.
Definitely advanced, but very useful tools.
Okay, SQL has clearly proven its longevity. It's been around for decades. But data and technology, they just keep evolving at this incredible pace. How is SQL adapting to new paradigms, like object-oriented concepts that are so prevalent in modern programming languages like Java or C++? It feels like upgrading our data bender toolkit from basic hand tools to these specialized, programmable machines capable of handling complex multi-component assemblies.
Exactly. The rise of object-oriented programming languages and the development tools definitely posed a challenge to the traditional relational model, which was really designed for simpler atomic data types, numbers, strings, dates. Objects in programming have complex structures, methods, inheritance, things that didn't map easily onto simple tables. In response, SQL and the databases supporting it began to evolve, leading to what we call object relational databases. These are hybrid systems. They extend the core relational capabilities to handle more complex data types and structures directly within the database, trying to bridge that gap.
So bringing object concepts into the database world.
Pretty much. Key object relational features that started emerging include user-defined data types or abstract data types. SQL has its built-in types. Object relational systems allow users to define their own custom data types. For example, you might define an add type that contains attributes like street, city, zip. Maybe the zip code itself is another defined type, postcode. This allows for richer, more structured data within a single column representing real-world objects more closely.
More complex building blocks.
Yes. And then tables within tables, nested tables and collections. This was a significant shift. Instead of columns holding only single atomic values, they could now contain more complex structures like collections or even entire tables. An end-of-year record, instead of linking to a separate degrees table via foreign key, might have a column degrees, which is actually a table of degree type, storing a collection of degree records directly within the engineer row. Also includes things like varying arrays. Arrays. Wow, that changes the structure quite a bit. It does. Also, large object support, LOBs, became crucial. Modern apps need to store images, audio, video, huge documents. Traditional varchar limits weren't enough. So BLBs, binary large objects, and CLOBs, character large objects, were introduced. These allow storing data potentially up to gigabytes in size. Systems like Sybase and SQL Server introduced text-y and image types for this. Because they're so large, you often work with them piece by piece using LOB locators, which are like pointers or handles to large data items stored elsewhere. And another feature, stored procedure overloading. Some systems allow defining multiple procedures with the same name as long as they have different argument types or numbers of arguments, like a getODTWages function that could handle different employee types, tech type, MGR type, with different logic, all using the same function name. Brings a bit of polymorphism, a core OO concept, into the database.
So SQL bending to accommodate more complex object-like structures.
Exactly. These features allow databases to model real-world entities more accurately, store richer data directly, blurring the lines between traditional relational storage and OO paradigms.
Okay, in today's hyper-connected world, data rarely lives in just one place anymore, does it? It's often spread out across many systems, different servers, different databases, maybe even different continents, different manufacturer systems too. How do we reliably bend and manage data across such a fragmented, distributed landscape? It seems incredibly complex.
It is one of the most complex challenges in modern data management, absolutely. The challenge of distributed data is significant. Data is spread across many systems, different vendors, potentially different versions. It introduces huge hurdles for maintaining data integrity, managing SQL consistently, ensuring decent performance across the whole network.
Lots of potential points of failure.
Exactly. Database vendors tackled this incrementally with a step-by-step approach. Initially, it was just tools to extract subsets of data from a central master database and load it into remote slave databases, maybe for reporting. Then came support for remote requests. A user on System A could issue a query directly against a database on System B. Usually each statement was its own transaction auto-commit mode.
Simple, but limited.
Right. Eventually, systems evolved to allow more transparently intermixing data from local and remote databases within a single query or transaction, making the distributed environment appear more unified to the application or user. To handle this, some practical approaches emerged. Superqualified table names and aliases. If you have tables named sales reps on both your local system and a remote system central host, you need a way to distinguish them. You might need a superqualified name like sample. That's central host Joe sales rep's name. That's obviously cumbersome.
Really long.
So you typically use synonyms or aliases, like create synonym remote reps for sample at central host or Joe sales reps. Then you can just refer to it as remote rep's name, much cleaner. Another huge area is replication and snapshots. These are about making copies of data strategically. Snapshots or materialized views. These are local replicas of remote data. They're periodically refreshed, maybe nightly. Good for performance as local queries are faster. They can be based on filtered data, e.g. snapshot of only high-value products, or even join tables from different remote sources, like creating a local sales team snapshot by joining remote sales reps and offices tables. They can even store pre-aggregated results.
So pre-calculated local copies.
Right. Then there's distributing the actual table data. Horizontal table subsets, sharding, dividing a table by rows. Different subsets live on different systems, like each distribution center database holds inventory only for its region. Vertical table slices, partitioning. Conceptually splitting a table by columns. Different systems might own different sets of columns for update purposes to resolve conflicts. Maybe personnel owns name address, while sales owns quote orders for the sales reps table. Mirrored tables, keeping identical copies on different systems. Updates might be routed based on rules, so e.g. customer names AM go to server 1 and Z go to server 2, to avoid conflicts while providing high availability.
Wow, it really is like coordinating multiple data vendors workshops across different cities. Clear rules needed for who handles what, how changes sync up, what happens if one workshop goes offline.
And that coordination, especially ensuring data integrity when a single transaction touches multiple systems, is precisely where the two-phase commit protocol comes in. It's absolutely essential for distributed transactions. It guarantees the all-or-nothing ACID property across multiple systems. If a transaction involves changes on server A and server B, a two-phase commit coordinates them. Either all changes commit on both servers or all changes are rolled back on both servers. Even if there's a network failure or one server crashes mid-process.
The bedrock of reliable distributed data bending.
Exactly. It's the critical mechanism for maintaining ACID properties when data is spread far and wide.
Okay, the internet, e-commerce, mobile apps, they've pushed data demands to just extreme levels, haven't they? Requiring split-second decisions, real-time responses. How are databases keeping ahead in this relentless race for real-time performance? It feels like the ultimate data bending challenge, processing maybe billions of data points in real time, like a live news feed.
The demand for speed has been a constant, powerful driver of database innovation for decades now. It's relentless. Back in the 1990s, OLTP, online transaction processing benchmarks like the TPC series, TPC-A, TPC-B, TPC-C, really push relational databases to achieve higher and higher transaction rates, handling more orders per second, more queries per minute. This drove significant performance improvements in core engine technology.
Competition driving innovation.
Definitely. And to cope with increasing query complexity on larger datasets, DBMS systems developed parallel query capabilities. On systems with multiple CPUs, SMP, symmetric multiprocessing systems, a single complex SQL query can be automatically split into multiple parallel execution paths. Different parts of the query run simultaneously on different CPUs. This can drastically cut down execution time. Our sources mention a 2-hour query potentially finishing in under an hour on a 4-way or 8-way SMP system.
Harnessing multiple processors for one big job.
Exactly. Allowing for faster business analysis, more sophisticated number crunching in the same time window. But the truly extreme demands, as you said, come from e-commerce and real-time applications. Peak load transaction rates for popular internet services can be, as our sources put it, 1 or 2 orders of magnitude higher than what conventional disk-based systems could handle. Just staggering volumes.
So how do they cope? What's the tech?
A major shift has been towards in-memory databases. These are increasingly used, especially for hot data, caching the data that's accessed most frequently. By keeping this critical data entirely in RAM, access times become orders of magnitude faster than going to disk. This allows systems to meet those insane peak load demands. It brings the data much closer to the customer interaction point within the network. Companies like Times and Performance Software, mentioned in the sources, specialized early on in these ultra-high-performance main memory database systems, critical where every millisecond counts.
Trading disk space for speed, essentially.
For the most critical data, yes. Another related area is data warehousing. This leverages relational databases, often specialized versions, for business intelligence, decision support, analyzing historical trends. You see concepts like star schemas used to model data for analytical queries, looking at data across multiple dimensions rather than optimizing for fast transactions. While warehouses often involve batch processing for loading data, they're critical for generating strategic insights from massive historical datasets, helping businesses understand what happened and why.
So different tools for different kinds of performance needs real-time versus analytical.
Absolutely. Meeting these intense modern demands requires not just smart bending, but lightning fast, parallelized, often in-memory operations across the entire data stack. It's a continuous pursuit in speed and scale. Hashtag tag outro.
Wow, what an incredible journey through the world of SQL and the art of data bending. That was quite the deep dive. From its fundamental building blocks, tables, keys, data types, and those critical ACID properties ensuring integrity, to the intricate dance of joins and subqueries for complex retrieval, and finally, exploring these powerful strategies for optimizing performance and adapting SQL for the future with distributed systems, object features, in-memory speed. We've truly seen how SQL lets us query, modify, shape, and extract profound insights from data.
Indeed, we've explored how a really deep understanding of these techniques allows you to truly harness the power of your data, transforming it from just raw material into actionable insights, making those complex data transformations, those bends, look effortless and precise when done right. It really is about empowering you to control your information landscape.
Yeah. And as data just continues to explode in volume, velocity, complexity, the art of data bending with SQL, it's only going to become more crucial, isn't it, for navigating our increasingly data-driven world. So here's a thought to leave you with. What unexpected insights might you unlock when you apply these techniques, these bending principles, to your own data sets? What hidden patterns are waiting to be revealed? That's all the time we have for this deep dive. We hope you feel more informed, maybe inspired, and definitely ready to explore these concepts further. Until next time, keep digging, keep learning, and keep shaping those data sets to your will. Remember, in the Data Benders workshop, the only limit is your query, so go forth and flex those SQL muscles.